First, tell me any one of you what is the meaning of vapor pressure of liquid? What is the meaning of vapor pressure of liquids? Okay, Ramcharan. Suppose you have taken the closed container like this, and we can say the vapor pressure of the liquid only in the closed container. If you take open container now, we'll say there's a boiling point of the liquid. Okay, there is a lot of difference between the boiling point and the vapor pressure. Suppose you have taken the container like this. I'll draw it somewhat neatly. Suppose you have taken the liquid like this. Okay, suppose you have taken one closed container initially, and we have removed whatever the air present inside the container with the help of the vacuum. Okay, with the help of the vacuum pump, we remove whatever the air present inside the liquid. Okay, because this is an empty space, right? Completely this part. So in this, initially, if you don't feel anything, air will be occupied. So now we have removed that air completely from the closed container with the help of the vacuum pump. Now, so whenever these two are there, some particles will be there in the liquid, right? So these particles, whichever is having the higher energy, will move from liquid state to the vapor phase. Understanding? Whatever the liquid particles are there, which is having the higher kinetic energy, will move from liquid phase to the vapor phase. So this particle will move from liquid phase to the vapor phase. Now, these particles cannot move outside, right? So again, whatever the particles are moving into the vapor phase, again they will come back and will exert some pressure. Vapor phase is nothing but the gaseous phase. Now gas will show some pressure on the surface of the liquid. Are you understanding? So whatever the particles are moving to the vapor phase, they will come back and will show some pressure on the surface of the liquids. So whatever the pressure created over the surface of the liquids in the closed container is called as vapor pressure. The statement is clear. The pressure exerted by the vapor on the surface of the liquids in the closed container at definite temperature is called as vapor pressure of the liquid. Any doubts in this? So this is the definition part. And today's class we have the theory only mostly. Okay. So after next topic, you have the numericals. The pressure exerted by the vapor on the surface of the liquid in the closed container at definite temperature is called as vapor pressure of the liquid. Clear now? So how this vapor pressure will be affected? So on what factors it will depends. The first one is the nature of liquid. Second one is the temperature. The third one is the impurities. So this impurities plays an important role in the vapor pressure. Again, impurities are two types. One is the volatile impurities. The other one is a non-volatile impurities. What's the meaning of volatile? What is the meaning of volatile?
amount of heat needed for something to boil.
The simple
Boil
which will evaporate easily.
evaporate.
The meaning of volatile is which will evaporate easily. Okay. Suppose if I have taken the petrol in the open dish, what will happen? It will evaporate easily, right?
Yes, sir.
But if you take the same water in the open dish, will it evaporate easily?
It will take time.
It will take some time. Okay. So volatile component is the one which will evaporate very easily, and non-volatile component is the one which will not evaporate. Okay. Now, so this vapor pressure will depends upon the nature of the liquid. That means whichever the liquid is less viscous in nature, which will evaporate easily, right? Because the particle will move easily in that liquid. If the particles are easily moving now, whichever the particle is having the higher kinetic energy, they will move into the gaseous phase. If more number of particles are moving into the gaseous phase, it will express more vapor pressure. Clear the statement? Next, temperature. When you increase the temperature, what is going to happen? The kinetic energy of the particle will increase or decrease?
It will increase when you
Increases.
increase the temperature.
When you increase the temperature, the particle kinetic energy will increase so that the particle will move easily from liquid phase to vapor phase, right? Yes or no?
Yes, sir.
If the particle move easily from liquid phase to vapor phase, whether vapor pressure will increase or decrease?
It will increase.
Increase. But simple, see here, simple logic you take here. Because the complete chapter, complete this topic will discuss only about this only. Suppose I taken one closed beaker, okay? And this is an empty space in the beaker, about this space. If more particles are moving from liquid to gaseous phase, what is going to happen? Closed beaker, right? Again, the same particle will exert the pressure on the surface of the liquid.
So the pressure will increase when there are more evaporating, vaporizing particles, right, sir?
Yeah, good. Simple, only one thing. If the more number of particles are moving from liquid phase to vapor phase now, those particles exert the more pressure on the surface of the liquid. So vapor pressure will be very high. If less number of particles are moving from liquid to vapor now, vapor phase now, less pressure will be exerted on the surface of the liquid. So vapor pressure will be low. Clear the statement? Any doubts in this?
No, sir.
If more particles are moving to liquid to gaseous phase, more vapor pressure. Less particles are moving from liquid to gaseous phase, less vapor pressure. Clear? Now, if you increase the temperature, obviously the particles will have the higher kinetic energy. That means they can move easily from liquid state to gaseous state. So if it moving to gaseous state easily now, there will be more vapor pressure. Clear? Okay, next, impurities. Now you tell me, if the liquid is more volatile, the vapor pressure will increase or decrease?
It will increase.
If the components of the liquid is more volatile in nature, the vapor pressure will increase or decrease?
Sir, as it will evaporate, there will be more particles evaporating, right? So the vapor pressure will increase, right?
Increase. Good. So because of evaporation, more particles will move into the gaseous phase. So obviously the vapor pressure will increase if the component of the liquid is volatile. What in the case of non-volatile? Due to having the non-volatile particles, more number of particles will not move into the gaseous phase, so that the vapor pressure will decrease. If you want explanation part for this, you just take one diagram here. See here, this is actually liquid. Okay, In this liquid, we have some non-volatile particles like this. Okay, the same diagram we'll take with one more here. So this is a liquid. There is no volatile particles. This is a volatile liquid. Volatile liquid. This is a non-volatile liquid. Okay. Now you tell me, in which case the more number of particles will move into the gaseous state? Here there is no particles, right, to stop the movement, right? In the case of this first one, there is no particles to stop the movement of the particles from liquid to gaseous phase. So more number of particles will move from here to here. Okay, then how we can show that one? Like you can draw the circles. More particles are moving. 1 minute. Hello.
Yes, sir.
Just wait.
Okay.
Can you see anything on the notepad?
No, sir.
Okay. So in the case of first, more particles will be moved from liquid phase to gaseous phase. But in the case of non-volatile liquid, there will be non-volatile particles covering the surface of the liquid, right? There will be non-volatile particles covering the surface of the liquid, which will not allow the liquid particle to move into the gaseous phase. Understanding the difference here. So that only few particles will move into the gaseous phase. Is it clear with the help of two diagrams? In the first case, it is a volatile liquid. So the particle will move easily from liquid phase to gaseous phase. So that there will be more vapor pressure here. Particles move from liquid to gaseous phase. So more vapor pressure. What about here? There will be non-volatile component which will cover the surface of the liquid so that the particles will not move freely from liquid phase to vapor phase. So that what is happening? Less vapor pressure. Did you understand these 2 points? Any doubts in these?
No, sir. Clear, sir.
Whenever you are adding the non-volatile liquid, what is going to happen to vapor phase? The vapor pressure will decrease, right? Okay. Whenever we are adding the non-volatile component, the vapor pressure will decrease. Just you remember that point alone. Fine. So from this, we can derive the equation for the Raoult's law. What is the Raoult's law? Anybody? The partial pressure of each component of the liquid in the given solution is directly proportional to the mole fraction of that component. Okay, the partial pressure of each component in the given liquid is directly proportional to the mole fraction of that component. So PS is the partial pressure of a particular component in the solution is directly proportional to the mole fraction. So if you remove this proportionality constant, PS equal to P naught S into XS. This is the Raoult's law. So if you want a definition part, the vapor pressure of a solution containing non-volatile solute dissolved in volatile solvent is directly proportional to mole fraction of that component. Okay, this is the actual definition, but if you want simple definition, what I said, the partial pressure of each component present in solution is directly proportional to mole fraction of that component. So your wish which one you can take. Okay, now is it clear? What is the PS? Partial pressure of component. What is the PS not? It is the vapor pressure of the pure component. It is very important. Vapor pressure of pure component. Next, excess. Mole fraction of that component. Okay, this is a Raoult's law, simple. Is it clear or not?
Sir, could you scroll up?
Finished?
Yes.
Okay. Now just you take, we know solution, right?
Yes, sir, you can move on.
Okay. So now if you take solution, it is equal to solute plus solvent. Okay. Solute will have the component PA and the PA naught, and the mole fraction is XA. Solvent will have the component PB, PB naught, XB. Yes or no? And we know mole fraction of the solution is XA plus XB equal to 1. Okay. Suppose if you write the Rolle's law for this equation part, what you will write? PA equal to PA naught XA, right? Rolle's law for this solute component. And the same Rolle's law will apply for this solvent component now. PB equal to PB naught XB. Did you understand why I'm writing like this? Understand or not?
Yes, sir.
Yes, sir.
PA equal to PA naught XA, PB equal to PB naught XB. Now we know Dalton law of partial pressure. P total equal to PA plus PB. Substitute the value of P total here. PA equal to PA naught XA and PB equal to PB naught XB. Now we know XA plus XB equal to 1. Can we write XB equal to 1 minus XA? Or we can write XA equal to 1 minus XB from this equation part. From this, mole fraction of the solution is completely 1. XA plus XB equal to 1, or XB equal to 1 minus XA, or XA equal to 1 minus XB. Just substitute the value of here. PA naught XA plus PB naught XB you can write as 1 minus XA. That means PA naught XA plus PB naught minus PB naught XB. So if you take common here, sorry, PB naught XA, right? So if you take XA and XA common here, what you will get? PA naught minus PB naught plus PB naught. So there is a P total, one formula for the Raoult's law. Compulsory, you have to remember this formula. Or else, instead of substituting the XB equal to 1 minus XA, we can substitute one more formula here. P total equal to PA naught 1 minus XB you can substitute in place of XA. Then PB naught XB. So what is the P total now? PA naught minus PA naught XB plus PB naught XB. Now XB is the common. So PA naught minus XB is a common. PB naught minus PA naught. That's all. So what is the P total? One more formula. PA naught minus PB naught minus PA naught into XB. Understanding?
Yes, sir. So this is the partial pressure, the total partial pressure, right?
Yeah, total pressure. See, total we have the
Total.
three terms. One is the total pressure. That's the P total is the total pressure. One is a PA, partial pressure. I don't know how many of you are understanding my handwriting. Next, PA naught, vapor pressure. So pressures are three types are there total. Total pressure, partial pressure, and the vapor pressure. So vapor pressure is possible in the case of closed containers. Partial pressure means what? Individual gas exerting some pressure in the container, right? That is a partial pressure. Total pressure means adding up all the partial pressures will form the total pressure. So this is a derivation part for the Raoult's law. So all the things you have derived only for last two formulas. You have to remember compulsory PA equal to PA naught XA or PB equal to PB naught XB, and the last two formulas. P total equal to XA into PA naught minus PB naught plus PB naught, or P total equal to, in terms of XB we want PA naught minus PB naught minus PA naught into XB. Please note down these two formulas first. Finished? If you finish this topic now, we'll start the ideal gas and non-ideal gas. Today's class is theory part only. Okay, shall we go to the next topic?
Yes.
Now, can you hear me properly?
Yes, sir.
Okay. So next one is the ideal solution and non-ideal solution. Okay. So ideal solution is nothing but, do you know ideal gas, right? Which are the gas following the or obeying Boyle's law, Charles' law, and Avogadro's law at all the conditions, that is a ideal gas. Similarly, we have the ideal solution also. So which are the solution obeying Raoult's law? Okay, which are the solutions obeying the Raoult's law at all the conditions, that is called as an ideal solution. What is a non-ideal? Solution not obeying Raoult's law. Simple. That is a non-ideal solution. Okay. So again, the non-ideals are two types. One is a positive deviation from Raoult's law. The other one is a negative deviation from Raoult's law. These are the two non-ideal solutions. So whichever the solution is obeying the Raoult's law, that is the ideal solution, and whichever is not obeying the Raoult's law, that is a non-ideal solution. So non-ideal solutions are again two types: positive deviation and the negative deviation. First, we'll draw the graphs for these two. Ideal solution. So if you want to draw the graphs, it will be looks like this. We derived the equation, right? Raoult's law. PA, PB, PB naught, PA naught, XA, XB, and all. Those terms we'll use here in the graph. So there is a mole fraction on the x-axis, and the y-axis it is a partial pressure, or you can take vapor pressure. So here the mole fraction of A component is 1. Here the mole fraction of A component is 0. Here B component is 0. Here B component is 1. That means the solute component is decreasing in the mole fraction, and the solvent component mole fraction is increasing. So what is going to happen between these two, that we are going to draw in the graph. So if PA is equal to PA naught XA, if XA is equal to 1 now, PA is equal to PA naught only, right? If XA is equal to 1, that means PA equal to PA naught. That means the vapor pressure will be maximum whenever the XA is equal to 1. So this is a maximum point. There is a PA naught point. Now, as the XA value start decreasing, then PA value also start decreasing, right? Yes or no? PA equal to PA naught into some 0 to 0.9 we are multiplying. That means the PA value will be less than PA naught value. So as you go down increasing, this graph also will come in the decreasing way. Whenever the XA is equal to 0, then PA is also equal to 0 because XA component is equal to 0. Now, next point. Initially XB equal to 0. That means PB also equal to 0. So it will start from here. What is this line? PA. So it will start from here. It will goes on increasing like this. Okay. Understanding the difference? XB component is increasing, XA component is decreasing. So this is a PB naught. So this is a graph. So when you add these two PA and PB, we get the P total like this. Do you understand the graph?
Yes.
Any doubts? Any doubts in the graph? Hmm?
Sir, I didn't get the PB is equal to 0 part.
See here. Initially at this condition, XB equal to 0, right?
Yes, sir.
That means PB equal to PB not XB. If XB equal to 0 now, PB also equal to 0 or not?
Yes, sir.
That means it is a 0. Now,
Yes.
XB is going to increase or not from 0 to 1.
Yes, sir.
That means PB equal to PB naught. Suppose XB equal to 0.1. That means PB equal to 0.1 naught of PB naught, right?
Yes, sir.
So it will increase like this it will goes. At one case, the XB value equal to 1. This case. That means PB is what here? If XB equal to 1,
Sorry, PB, yeah, times.
PB naught. So this
PB.
value is PB naught. Understand? Now, how you are obtaining this line now? P total means what? PA plus PB. So when you're adding this point and this point, we'll get only this point. But when you're adding this point and this point, this and this, we'll get sum of this, right? Sum will be this. When you're adding this and this sum, we'll get the sum is this. Understanding?
Yes, sir.
When you're adding this sum and this sum, we'll get the sum like this. Clear now? Is it clear?
Yes, sir, it's clear.
So this is the ideal gas curve. Sorry, ideal solution curve. Next, when we come back to the non-ideal solutions, we have the two curves. So non-ideals again two types. One is the positive deviation. The other one is a negative deviation. But whenever the ideal solution is showing, it has the three important conditions. So any solution to show the ideal condition for ideal solution. First one, delta H should be equal to 0. The change in enthalpy should be equal to 0. The change in volume should be equal to 0. These are the important conditions for the ideal solution. Whenever these values are equal to 0 only, the solution will behave as an ideal solution. The third one, it obeys Raoult's law. Next, I said one thing here. Where is that solution part? Okay. If you take solute plus solvent, it will only form the solution, right? That means solute if you take AA and solvent if you take BB, then what will be the solution?
AB.
AB. Good. See, AA will have the type of intermolecular force, right? A and A binding means they have an intermolecular force. Either it can be ionic bond or the covalent bond. B and B also binding now. It is a one type of intermolecular force. So that this AA and the BB intermolecular force should be similar to AB type of intermolecular force. Then only it will obey the ideal gas condition. AB intermolecular interaction should be similar to AA and BB intermolecular interaction. Okay, then only it will follow the ideal solution. So these are the four important conditions required for the ideal solutions. Delta H should be equal to 0. What is the meaning of delta H? What is the meaning of delta H?
Enthalpy.
Enthalpy change. So change in enthalpy should be equal to 0. Change in value should be equal to 0. It should obey the ideal Raoult's law. AB intermolecular force should be equal to the AA and the PB type of interaction. Okay. So next one is the positive deviation. Positive means what? Delta H not equal to 0. Next, delta V not equal to 0. Now, the vapor pressure will be higher, right? Suppose I have taken one graph here like this. And then we have taken the solution. So this is the first BB component is there. And next we are taking the circle particles. It is a AA. Now if you want to show the more vapor pressure, the AB should be stronger or weaker?
Should be weaker,
Why?
so that if there's more vapor pressure, that means the particles intermolecular strength is less, so that it can evaporate easily, so the vapor pressure will be more.
Very good. Whenever the AB molecular bond is weaker, it will break easily. If it break easily, it will go into the gaseous phase easily, right? So that it will show more vapor pressure. More vapor pressure than the ideal solution, positive deviation. Understanding the point? If AB is weaker than AA and the BB, then the vapor pressure will be higher. It will show the positive deviation from the Raoult's law. This is a very important point in the positive deviation of Raoult's law. Is it clear for everyone?
So if AB is weaker than AA and BB, it will show the positive deviation. But why will it show positive deviation? Positive deviation means that the vapor pressure is more or less.
Vapor pressure will be more. I will draw the graph that one. Wait 1
Okay.
minute. So same graph will follow here. So you know already how we got this ideal solution graph, right? This is the ideal solution graph. X A equal to 1, X B equal to 0, X B equal to 0, X B equal to 1. Now, if the vapor pressure is more now, this is a PA component, this is a PB component, this is a P total. Then positive deviation means what? PA is showing more than this, like this. This or no, this is a line, this is a positive. If this is the line, now what is the positive? PB? Is it this or above? Which color we have to draw? Red color or violet color? If PB is showing the positive deviation, which line we have to draw? Either violet color line or the red color line? The red we have to draw, right? Positive means above line, right? This is the main line. We are drawing above line. That means the overall pressure, what will happen now? It will show more than the ideal solution. This is the positive deviation.
So is this like an ideal curve? Like how like ideal gases will have less, like there's a line for ideal gas, how it acts, and then like the nitrogen and carbon will go under it. Their curves will be under and then go up.
Good. That ideal solution curve is this, the straight lines only.
Okay, sir.
But if you are deviating from the ideal now, this is the ideal deviation, right? This upper curve, this is the deviation part. Here the deviation part is this, the black line which I am drawing now,
Deviation, all the curves will go above the ideal.
above the ideal. The same thing, if you go for the negative deviation here, so again the same, this is ideal first, we'll draw the ideal. PA naught, PB naught, join these two. And sorry. Okay, now this is XA equal to 1, XA equal to 0, XB equal to 0, and XB equal to 1. This is a mole fraction, everything you know already. Now this is a negative deviation, right? Negative deviation now, what you have to take here? This is PA, this is PB. Okay, if it is a negative deviation, what we have to follow? Below, right? The vapor pressure will be lower than the ideal. This is ideal. Black line is ideal, but the vapor pressure is lower than the ideal, right? If this is a line, if this is the line, this will be the lower vapor pressure, right? Understanding? Now, both the vapor pressure components are lower. Obviously, the final components also will be lower than the ideal. So whatever the orange color you are seeing, that is a non-ideal, negative deviation. Clear? Anjali?
Yes, sir, clear.
So this is a positive deviation graph, this is a negative deviation graph. Okay, now tell me what is the condition for the negative deviations? One by one. Again, delta H not equal to 0, delta V not equal to 0. Now tell me AB type of interaction should be stronger or weaker? AB interaction should be stronger or the weaker?
It will be stronger, sir.
It will be stronger. Good. If it's strong only, it will not break easily, right? If it won't break easily now, it will not move from liquid phase to gaseous phase easily. So AB interaction should be stronger than AA and BB. Okay, so these are the important conditions for the negative deviation. Any doubts up to this? I don't know how many of you are understanding, but only one person is replying in the class. What about the remaining people?
Yes, sir.
One second. The conditions for the negative deviation, could you show?
Sure. Yeah. What about the remaining people? Just respond first. Desha, Dhairya, Divya, Jafar.
Yes, sir.
Clear?
Yes, sir.
What about Vishwanath, Varsha? Varsha, you're the new, right?
Yes, sir.
Yeah. Can you introduce yourself? I mean, you're in the class, current class 12 or going from class 1 to 12?
So class 11 to 12.
Class 1 to 12, good. So don't worry, again, we'll study the same topic. We have a regular classes set in that again we'll cover with the theory part and all. Next, what about the Divya, Jafar, Neha?
We're done.
Yes.
Clear?
Yes, sir.
Anjali, what's the doubt?
No, sir, you can move on. Proceed. Next.
So these are about the ideal solution and the non-ideal solutions. Okay. So in the exam point of view, actually they'll ask for the examples only. About this, they'll ask these conditions or they'll ask the examples that you have to memorize completely. There is no shortcut trick and all. So first I'll write the ideal solutions here. So these are ideal solutions. Next, non-ideal two types, positive deviation and the negative deviation. This table you have to memorize completely. First one, hexane plus heptane. Can anyone of you tell me what is the hexane formula? What is the hexane formula? Guys, come on. It's alkane, right? Studying from the class 10th. It's okay if you tell the wrong also, I will not tell anything. Don't worry. But give me the reply. What is it? See?
H14.
C6.
H14.
Good, correct only. C6H14 is a hexane.
Yes.
Yeah, Desha. Correct. So these are the examples. Compulsory how to remember these. There is no other go. So first ideal solutions are what? Hexane and the heptane. Next, ethyl iodide and ethyl bromide, benzene and the toluene, chlorobenzene and the bromobenzene. So chlorobenzene, bromobenzene, benzene, toluene, ethyl bromide, ethyl iodide, hexane and the heptane will form almost the ideal solutions. Next, positive deviation. This is a non-ideal solution. Acetone and the CS2, acetone and the C2H5OH. What is the name of C2H5OH? What is the name of C2H5OH? No reply.
Ethanol, sir.
Phenol.
Ethanol, sir. Ethanol, sir.
Phenol. Okay, good. Phenol formula, can you tell me?
Sir, ethanol only.
Phenol, phenol.
C6 H5OH, sir.
C6H5OH, good. The structure will be like this, right? This is the structure of phenol. Okay, so these are the examples for the ideal and the non-ideal. So ideal case, hexane, heptane, ethyl iodide, ethyl bromide, benzene and the toluene, chlorobenzene and the bromobenzene is the ideal solutions. Next, non-ideal, positive deviation and the negative deviation. Positive deviation is what? Acetone and the carbon disulfide. Next one, acetone and the ethyl alcohol or the ethanol. Water plus ethyl alcohol and water plus methyl alcohol. These are the positive deviations. Negative deviation is what? Acetone plus aniline, water plus HCl, water plus HNO3, acetic acid plus pyridine. These are the negative deviations. Okay, so these are examples you have to remember compulsory. So any doubts in this? Any doubts?
No, sir.
No, sir.
Okay. So next topic is the azeotropic mixture. First, do you know what is the distillation process?
Yes, sir.
Can you tell what the process means?
So conversion of liquid into water, then again the condensation occurs in that distillation,
Okay.
obtaining pure water.
Wait. What is important?
Mainly obtaining pure substance from that, or separating two substances like compounds from each other, or components of that.
Wait. Generally, which are the two components of the liquid? We cannot separate the two liquids, right? Easily. Like if you are mixing the alcohol with
No,
the
sir.
water, we cannot separate that one. Or when you are mixing the water and the milk, we cannot separate that one. So in that cases, if the two liquids have a different boiling point, we can use the distillation method. Based upon the boiling point, whichever is having the lower boiling point will evaporate easily and we can collect into the another container by condensation process. And whichever the liquid is having the higher boiling point will stay in the same distillation flask. That is what the distillation technique. But what is the definition for the azeotropic here? Azeotropic mixture. It is a mixture of two liquids which has constant boiling point and has the same composition in the liquid and in the vapor phase. Okay. Azeotropic mixture is a mixture of two liquids which will have the constant boiling point and also will have the same composition in the liquid phase and in the vapor phase. That means we cannot separate this mixture using the distillation technique, right? Yes or no? We can't separate this mixture using distillation technique. 1 minute, please. Okay. So again, we have the two types of azeotropic mixture. One is a minimum boiling azeotrope. The next one is a maximum boiling azeotrope. So whichever the liquid showing the positive deviation from the Raoult's law, that will show the minimum boiling azeotrope, and whichever is showing the negative deviation from the Raoult's law, that is a maximum boiling azeotrope. Clear? The liquids which is showing the positive deviation from the Raoult's law is the minimum boiling azeotrope, and the liquid which is showing the negative deviation from the Raoult's law is the positive or the maximum boiling azeotrope. So with this, we'll end the topic here. So today's is a complete theory part. So next we'll start with the problematic part in the colligative properties. Okay.
Sir, could you show the examples of ideal and non-ideal once again?
Yeah.
Yes, sir. Could you give me 1 minute? I'll just copy.
Sure. So just take the screenshots. Or else I'll upload this in the Google Classroom, right? The notes.
You can continue. I took screenshot of it.
Yeah, sure. You can take this also. Next. Any doubts in today's class?
No, sir.
Okay, fine. We'll end the session here.